Hey everybody, this is Larry. This is day 415 of the Leetcode. I don't know why I need to know. I don't know why I didn't. I don't know why I needed the computer to load the date to tell me the date, because I know what day it is. Come on. It's also on the computer. Anyway, hit the like button, the subscribe button, join me on Discord. Let me know what you think about this one. We have 24, 29 minimum. I don't know why I'm doing this video. I clearly cannot talk today, or even think maybe. We have minimize XOR. Let's go. Let's go. Given two positive integers nums1, nums2, or num1, num2, find the positive integer x such that x has the same number of set bits of s num2, and the value of x XOR num2 is minimal. That's kind of weird, right? I mean, it's weird. I mean, it's a little bit weird only because num2 doesn't have anything other than it's just a number of set bits, right? Like yeah, it could be a number from 1 to 30 and it wouldn't change anything, which is kind of why it's a little bit weird to me, but it's not that bad, I suppose. I'm just saying. Okay, let's actually think about this, right? Well, first, I guess let's just say maybe you could write something like hope my computer's okay today. I am running something in the background, that's why. But yeah. Anyway, there are I think different languages have either something similar, but it's also a for loop, right? So it's not that big of a deal. I just wanted to make sure that this works because I always forget if it's bit count or bit underscore count, right? See, so yeah, which is kind of a very awkward thing, but it is Pythonic. It's just I don't know. In any case, yeah, so that's number bit, and then now we have to actually think about a problem because I don't know what's going on here. Okay, so so we want a number x such that it has b number of bits, and the XOR is minimal, right? Well, how do we make it minimal? I think the idea is, okay, well, I mean, I think I know how to do it. I'm just trying to figure out a way to articulate it, right? And the thing with these things is that, just knowing how to do it is fine. And if this was a contest, I would be cranking it out. But I'm also trying to, articulate and explain a little bit, or at least convince you a little bit that it works, right? Or at least, convincing myself that I've convinced you, which is maybe not the same thing, but that's besides the point. Okay, so we want something that with xbit. I think the first thing that we might do, right, is well, what is the smallest number that can happen, right? I think that's maybe an idea that we would explore and think about, right? Bitwise functions are always a little bit tricky, I think. But in this one, there is this sort of greediness, right? And when I say greedy, I don't know if greedy is the right term. It doesn't feel 100% the right term. But the idea here is that when you have two numbers, only the most significant bit matters, right? Like if you're comparing between two numbers, the most significant bit is the bit that matters. Of course, there's tiebreaker that you can think of it recursively almost, right? But that's the thing, right? So that means that, and what I mean by that is that if you have a 1 very early on, it doesn't matter what the rest of the numbers are, right? It could be all 1s, and this is obviously still smaller than this one. So that's kind of the train of thought that I'm trying to get across, right? A train that I'm trying to get across? I don't know. Is that a phrase? Sounds terrible. In any case, yeah. So I don't know. I think I have a couple of ideas, and as they are greedy, it is a little bit tricky, right? Yeah, because the idea here is that it almost feels like so we have a set number of bits, and obviously. If you try to do something brute force, it's probably not going to be very fast, right? Like there are 30 bits within the constraints, it goes to 10 to the 9. And if there are 15 bits, then it's 30 choose 15, which is actually a very big number relatively, right? Is that true? Am I lying to you? Okay, I mean 115. I guess is actually not relatively not that big, but still too slow for this problem, I believe. Yeah. So I think the idea here is, in a way, kind of going back to what we had with the ones and zeros here, right? Is that I think okay, maybe this is the right way to explain it. Is that in a way you're going to ask yourself, okay, huh? I actually just maybe have something. I don't know. But that's actually interesting. Well, what I was going to say is that I didn't actually think of this. There was like a shortcut. I was going to write this out as a more of an algorithm, but I think I don't know if I'm right, that there is an observation which I will make later. But anyway, my idea is that okay, well, let's start with num1, and we have the number of bits, right? So maybe I'm just banging on the keyboard. Really, this is a random number, effectively, right? And then the idea here may be that okay, we can say okay, if we set this first digit to 0, can we still like make the number of bits here like, so this is actually number 1, right? Just to be clear, is there a number that we can XOR by with b bits where this will be 0, right? And of course, there are ways to think about that, which I'll talk about in a second. And then, if the answer is yes, then the first digit is 0 and the answer. And so forth, right? Well, we return the x or the, oh, okay, no, we don't return the y, we return x, but that's an easy operation, right? And then the second thing then, and maybe that, okay, well, the first digit is 0, or maybe, maybe your thing is that, okay, the first digit has to be 1 for whatever reason. The whatever reason I'm skipping for now, we'll talk about that in a sec, about how to check this thing, right? Well, if that's the case, then you go, okay, well, if the first digit is 0, can the next digit be 0, right? And so forth. And that's really dot. And even if the first digit is 1, you're still trying to minimize. It's just that the first digit is forced, right? So then you're 0 and 1 and 0, 0, 0, right? Whatever. You just try to figure out one digit at a time where the rest is possible. And if you do it in a funky way, I think maybe you could do it like n squared, n cubed, keeping in mind that this is a binary number with a binary digit where n is not the input, n is actually the number of bits representing the number. So that means it's 30. So that means that n cubed is 30 cubed, which is fast enough for most parts. Even if you had it at, like, these are the things I would think about. Like, I don't know that I have an n squared algorithm to check for every digit, but if you did, that's okay. That's what I'm trying to say. And by looking at it this way, it gives you a lot of flexibility, right? Because you could do n cubed and maybe even n to the 4th. I can't do math, so I don't know what that is. 30 to the 4th. And yeah, 30 to the 4th is less than 1,000,000, so even that would be fast enough. So it opens up a lot of ideas that we can play with, especially if you're on a contest timing, right? I think one thing that I didn't notice is that, okay, so for every digit, you can maybe even write out a truth table, right? So we only look at one digit at a time. So we have num1 and then maybe possible num2, right? So these are actually only 2 columns. So here, and then maybe the n with, oh, sorry, not nums2, sorry. This is x in the notation, and then num1 XOR x, right? So then now you have 0, we have 0, then this is gonna be 0. I mean, I don't really need to write out this out for y'all, maybe not, but oops, but I am anyway, so yeah. Okay, so what is the idea here, right? The idea here is going to be, well, greedy, right? If we look at the number 1 digit at a time, we can see that if the first digit is 0, we want to make it 0. If this is a 1, we want to make it a 1. And then we just keep going. So that's really the idea. That's pretty much it, right? And it uses up one to b. And then the other thing that we were talking about earlier is that, well, this is only a choice if we have enough digits in the rest of them to go, right? Because, okay, so basically here's the optimization, right? Is that, well, in a greedy way, we want the first digit, or the current digit, if you will, to be a 0. So let's move this up. Oops. So these are the two things that we want that to happen. Of course, if we see a 0, then it doesn't cost us anything, right? If we are able to. The only other case that happens is that, well, this is, oh yeah, and let me just be exhaustive anyway. And if we have any digits left of B, then if we see a 1, we want it to be used up a 1. Also sensible, because this will always allow us to minimize minimization, right? And we have no choice here, really, because it doesn't make sense to quote unquote save this for later, because if this is a 0, then you basically have this one, and then this is a 1, and then like we said earlier, it doesn't matter what the rest of the number is, this number will be more suboptimal, which is where the greedy comes from, right? Okay, so then now, when would we do this? Well, this case, I think in a case analysis kind of way, we could have worked it out in another direction, but nonetheless, now that we're here, it's still the same, right? Which is that if the 0, when would we need to, we would never willingly choose a 1. Well, the willingly is the key word in that statement, because if you, if you don't have enough digits left, then this has to be a 1. So that's really the idea behind this problem, and that's it. That's it, right? Because if this is 1, and obviously you would always match a 1 with a 1 if you have B, if you have digits left. If you don't, then you also have no choice, because you just don't have any digits left. And that's okay, because presumably you used the digit up earlier on as part of the greedy kind of inductive kind of reasoning, right? So even though we did not optimize here, we ran out of digits, so it is what it is, right? So that's basically the idea that we're trying to do here, and now we can, well, figure it out, right? So yeah, so then now we can do things like, and this is actually gonna depending on how you want to write this, you can actually clean this up a little bit. Yeah, I'll explain what I mean after I kind of write this. So let's say we have 30 digits. Actually, and we want to go, go from top to bottom, because as we said, that is the most significant digit, right? So then we just have to kind of implement this idea, right? So where B is the number of digits. What are we doing? So we're returning X, right? So that means, yeah, we have to set X. So yeah, so basically we just look at the number 1 digit at a time. You can also use a string if that's what you're more comfortable with, like a binary string. I don't know, it's just language, right? So I don't know, this is a bitwise function. So then now you just check if this digit is turned on, right? So if this is greater than 0, then this is a 1. And if this is a 1, then we have to use up a B. That's what we said, right? So yeah. Well, if B is greater than 0, then we use up a digit, which means that for X, which is the answer, we decrement B, we flip X, oops, and that's it, right? Else, well, you have no choice, so you don't change anything with X because you can't use anymore, right? Okay, so otherwise, if it is 0, then we just, then what happens? Well, there are only two choices. One is 0 because we're good, or if we're forced to use a digit, then we have to use a digit, right? So that means that if B is, it should be, in theory, because of the way that you set up the invariant, it cannot actually be greater than, and that is like, what, intermediate value theorem kind of thing, right? Because what I was going to write is something like this for some k, we decrement by 1, but that would mean that this will always happen first, as long as B is bigger than number of digits left, right? So you can write it either way, is what I'm going to say. But what is k, right? So if this is the case, we're forced to use 1 as we had before, and that's it. That's the entire problem. We have to write this k though. So what's k? K is just the number of digits left, and the number of digits left, let's just say maybe we can even write like m is equal to, oops, just so that if we have a fewer constants, right? M is 31, And then now, yeah, m minus I is the number of digits, right? Left, yeah. And I think we are good. Let's run it real quick. And I think we are wrong. Did I miss a case? Oh, if it's a 1, we have to do a 1. If it's 0, we have to do a 1. If it... No, I mean, I think those are the 2 cases. I don't know why this is so wonky. Did I do them in a weird way? I mean, it was outputting the same thing. So, I am definitely doing something very weird. So, okay, so if this is 0, if b is greater than m minus I, then we're forced, right? Alright, well, did I just... Maybe I just do something funky. Okay, so it's all happening here, which is also weird. Well, maybe not. Maybe we just have this. Oh, well, now it's gonna get... Yeah. Huh. Honestly, I don't know. This is why my rating's been terrible lately. I don't know why these things keep happening. But, wait, is it bit count or ones count? Maybe that's why. Did I mess this up? No, this is 2. This is 2. Is 12 2? 12 is 2. Yeah. So that's not wrong. Let's see. B M I 231. Did I mess this up? I mean, this is... Oh, I'm dumb. I forget that I is we're counting down, right? So this is going to be 0 to begin. I think this is one of those things where when you have too much experience, sometimes you auto plug in things without realizing, almost like you're auto completing, and I just wasn't thinking about it. All right, so that means that the number of digits left is actually I, right? So that's actually way easier when we go backwards. I'm just being dumb. Am I off by 1? Yeah, okay. I guess that's it. Because when I is 0, there's 1 digit and you need to do it. Okay, yeah. So that's really it. Despite the silliness and whatever. Let's give a submit. And yeah, 1751 day streak. Have I done this before? I don't remember this at all. Though I guess I did the same way. Actually, I thought about doing it this way, actually. But, yeah, well. But yeah, hopefully this makes sense. And yeah, what I was going to say is that what is the complexity of this algorithm, right? This is actually m squared, where m is the number of bits or whatever, right? Because this is O of m and this is also O of m, right? Because you have to shift m times in the worst case. So this is m squared. However, there are ways to make this O of m. And the way to make this O of m is just, well, reverse the number of bits. And so then you could do this 1 by 1 without this shift. You can just, take it, do a shift. And if you reverse and then you take the last bit, because your most significant bit is your last bit now. So you reverse the bits, you do the math, and then you reverse the bit back. So that will give you linear time, which is O of m. Yeah, and that's all I have for this one. Let me know what you think. I know this video is a little bit long for what it is, and I think probably a lot of people could intuit the solution. But I want to also just highlight what it means to have a greedy idea and kind of just break it down a little bit today. Just to, I don't know, maybe it's a little bit verbose. Let me know in the comments what you think. Maybe I could have done this in a faster way. I don't know. Thanks for watching though. Hope Wednesday is good to everyone. Both Wednesday and Wednesday on Gen 15. So that's like middle of the day. Oh, sorry, middle of the week and middle of the month. Anyway, I don't know. That's... Anyway, thanks for watching though. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.